So we've seen a number of properties that the Brownian motion has, including the Markov property, the Martingale property, but we've seen the transition density and so on. However, there are kind of two definitions of the Brownian motion to be aware of that are useful for various problems, and the two definitions kind of work depending on the problem setting. And here is the first definition. So the first definition states that a standard Brownian motion is a unique process with continuous paths. So continuous paths is not to be confused with continuous time, even though that's certainly the case here. Continuous paths means that you draw it on a piece of paper without lifting the pencil. And these paths all start at 0, and they satisfy two properties that involve the increments of the process. So this is what I'm going to spell out the details of, but said briefly, we're going to claim that each increment is mean zero normal with variance that equals the length of the interval, and that these increments are stationary and independent. So let's get into some of the details of this. So first of all, any process, and this is not just about the Brownian motion, any stochastic process may always be written as the sum of its increments. So what I'm starting with here on the left side is the process x at some time t, and what I will do is just subtract and add the value xs, leading to x at time t being expressed as x at time s plus the increment between time t and s. So here the t and the s don't even have to be ordered, but let's assume that, because when we say increment, we really do mean that it's the difference between the process at two times, one time being in the future and one being in the past. So here we're thinking of the following order for the times that are involved, and the time u is going to provide one more increment. So moving from this expression here, we move on to add and subtract an x at time u, leading to x at time t being expressed as x at time u plus two increments, one from time u to time s and the other from time s to time t, and so on and so on and so forth. And so not surprisingly, you can do this pretty, for any kind of general number of time stamps. So if you have n points in time, you can then write your process as a sum of all of these increments. And one thing to be wary of is never to forget kind of the starting value here. For the Brownian motion, this in fact is disappears because of the property that says that we start at 0. But more generally, if we're thinking about any process, then this formula here would work in general. And this brings us to the definition of what it means to say the increments are independent. And this again is a definition applied to any process. If its increments are independent, then they would have to satisfy the following property, meaning that the probability that the joint distribution of the increments must equal the product of the marginal distributions. So that's what it means for some number in here m of random variables to be independent. It's just that their joint distribution is equal to the product of the marginals. So the definition kind of stays true to its word. The second part of the definition had to do with stationarity of the increments. So if we go back up a little bit here, what I just covered is the independent part of the increment. And now we're going to look at what it means for an increment to be stationary. And by increment, we again mean a difference of the process at a future value minus the one at the past value. So independence of increments was covered here. Here we're going to look at stationarity of an increment. And for this, it's helpful to define the increment of size h. So x subscript h is going to denote the increment of the process x, the increment length the duration of the increment is here equal to h, and the past value, or at least the starting point of the increment is t, and the end point of the increment is t plus h. So what does it mean to have, for a process to have stationary increments? It means that the probability distribution of the increments doesn't change based on the location of the increment. It's only a function of the length. In other words, when the length of the increment is the same, namely if we fix this h to be of some value, we can choose the starting point of the increment, in this case s, and t to be anything we want, and these two probabilities, these two probability laws or cumulative distribution functions, they are the same. So stationarity means that the probability law, or the probabilities assigned to these increments, don't change based on what time point you look at the increment at. As long as the increment has the same duration, the length, h, the probability law should stay the same. So that's what it means for the increment to be stationary, and here I just wrote out the definition in a little bit more detail. So you see the increment is there on both sides of the equation, but the difference, of course, is the starting point of the increment. On the left-hand side, the starting point is t. On the right-hand side, the starting point is s. And as long as, again, the length of the increment, which is h in both cases, is the same, then these probabilities must be the same when the increments are stationary. So simple enough, and hopefully the name stationary kind of makes some sense here, in the sense that it's not changing, right? It's not changing for the different starting points of the increment. And here's the summary. So we just have to kind of unpack this definition here. Here's what it comes down to. The increments must be independent. And so you take a collection of m increments and you look at their joint distribution. For them to be independent, that has to equal the product of their marginals. So that statement is true by the definition, or that's the unpacking this part of the definition right here, the word independent. Then the next thing has to do with stationarity of the increments, and that's written right here. So for all s and t, regardless of the starting point, as long as the duration of the increment is the same, in this case h, the probability distributions don't change. And the last part has to do with mean zero normal with variance, that's the length of the increment here. So this last integral is reflecting the fact that every single increment has a distribution that is normal with zero mean and variance equal to the length. So how does this work? If we look at this density here, it's precisely what it is. This is the density, the probability density function of a normal random variable with variance equal to h. H here is the length of both of these increments, the one from t to t plus h and the one from s to h. The mean of this density, or the mean of the random variable corresponding to this probability density function is 0, because you just see x squared in the numerator there, not x minus some mean. And I think that about sums it up. I think we've checked off all the boxes: the independent, the stationary, and the normality part, the actual distribution of that increment. So this is the first definition. Let's look at definition 2, which is also useful, and you kind of want to go back and forth between them depending on what the problem at hand requires. The second definition starts off in the very same way, but now the conditions are going to be a little bit different. So the two kind of items that we have to check off look different than before. Before there were conditions on increments. Now the conditions have to do with something called the Gaussian process. This is covered in Ross, and I'll describe this as well. And also something called the autocovariance function here, which is just the covariance of the process at various points in time. The word auto here refers to the covariance of the process with itself, and that just means taking the process at different time points and saying what the covariance is between those two values in time series. So we first have to look at what it means to be a Gaussian process. So Gaussian processes are more general than the Brownian motion. The Brownian motion is just an example of one, but the general definition of a Gaussian process is something for which a vector of this form. So in other words, we have a process X, and we're going to pick n timestamps, t1 through tn, and we're going to form this vector, so it's a vector xt1 all the way through xtn. If this vector has the normal multivariate distribution, then the process is said to be Gaussian. So what does it mean to have a multivariate normal distribution? This is a shorthand way of writing it. This is the notation. So this would be a multivariate a normal distribution with a mean vector mu. So this would be a vector of means for each coordinate. So the first entry of mu, say mu1, would be the mean of xt1, this random variable. Mu2 would be the mean of, and by mean I mean expected value, of xt2, and so on and so forth. And then the second part refers to a covariance matrix. So if you have a multivariate normal, this is a multidimensional object, and so it has an entire covariance matrix that describes not only the variance of each of the random variables, but also the covariances between each of the coordinates. So in other words, the diagonal entries of this matrix sigma are going to correspond to the variances of each of the coordinates. So the very first diagonal entry of sigma will be the variance of xt1, and so on and so forth. The very last diagonal entry of sigma is the variance of xtn, and the off-diagonal entries would correspond to the covariances between each of the coordinates. So I wrote this right here. That's the formula for the covariance between coordinates I and j, and the formula on the right hand side just computes that covariance between those two specific random variables, in one case xti and in the other case xtj. This expression here, it's a little bit involved, but it should remind you of the normal distribution in one variable. This is the extension of the same idea to a multivariate probability density function. So you can see that instead of the variance ending up in the denominator here, you actually have the determinant of the covariance matrix ending up under that square root. And instead of dividing by the variance of the random variable, you have the inverse of the covariance matrix. So this is a generalization of a normal random variable that has n components. And the reason you need a whole matrix for this is that not only do you need to describe the variance of each of the coordinates, you also need to describe the covariance between them. In other words, how are they statistically correlated with one another? When the coordinates are completely independent, say the xt1 is independent of xt2 and so on, the off-diagonal entries of the matrix sigma would all be 0. But and you can check that directly from this formula, right? As soon as those things are independent, you have the expectation of the product is equal to the product of expectations, and each of those expected values taken separately is 0. So you'd have a diagonal covariance matrix. Now the final thing to mention is that the multivariate normal random variable xt1 through xtn can always be written in terms of a collection of independent, identically distributed normal 0, 1 entries. And so what you need, in other words, is, or I guess not what you need, but what you can claim is that any multivariate normal random vector can be written in the following form. It'll be written as a vector of the means plus some matrix A times a vector V, where the vector V contains a bunch of independent normal 0, 1 distributed random variables. And so what this term is doing is in fact taking linear combinations of these normal 0, 1 entries, and in effect that creates the correlations, if there are any, in the components of this vector. Last thing, when we say mean 0 Gaussian, we are referring to the fact that, at least for the Brownian motion, the mean of the distribution of a vector at any number of time points is 0. So, just looking at this definition again, right here, the mean would be 0, and for the Brownian motion at least, you would be able to write it as a linear combination of a bunch of normal 0, 1 random variables, leaving some, leaving possibility that there is a correlation over time. So this function right here is actually describing the entries of the covariance matrix in the case of the Brownian motion, and that's what we're going to look at here. So let's see. So for the Brownian motion in particular, not for a general Gaussian process, if you have a bunch of timestamps, t1 through tn, and you create this vector, this n-dimensional vector, the distribution of it will have mean 0 in every single component. So the expected value of every single WTI is 0. And it will have an n by n covariance matrix, sigma, with the following entries. So in other words, the off-diagonal entries for I not equal to j, those will not be 0, which basically tells you that over time, the Brownian motion is correlated, where the process was at timestamp 3 and where it is at timestamp 4. Those two quantities as random variables are correlated. One has impact on the other. And in the specific case of the Brownian motion, this covariance is given by the smallest value between the two timestamps. So if you are comparing WTI and WTJ, the covariance between the two is equal to the smaller of the two time values. So Ti is smaller, this expression would equal Ti, and if Tj is smaller than Ti, the expression would equal to Tj. And you can very quickly check for yourself that if I were to input I equal to j, meaning ask what is the variance of the variable WTJ, same as asking what is the variance of the variable WTI, that right away gives you Ti or Tj, those are the same. And that is in fact the same definition that we had originally when we derived the density of the Brownian motion at any point in time. So, the one kind of question to check or to look into is whether the two definitions imply one another. We're going to look at one of these, one direction in which you would check this. So, because both define the Brownian motion, one should imply the other, and the other should imply the original. So we're going to check whether definition 1 implies definition 2. And for that, we need to actually state what the definitions are again. The first one characterized the Brownian motion in terms of a continuous process starting at 0 with increments that have certain properties. One of them had to do with the fact that each increment is mean 0 normal, and the other property on the increments had to do with their independence and stationarity. The second definition kind of disregarded the increments, but imposed this Gaussian process condition, and also it involved a very specific form for the covariance function. So each, given a description of any process, provided that you can check off either these two boxes or these two boxes, you have a Brownian motion on your hand. So suppose we're given some process, let's call it W, that satisfies definition 1. So we're going to assume something that satisfies definition 1, meaning these two properties related to increments. The question is, can we then verify these two properties to make sure that it satisfies definition 2? Well, I said here, let's take the last part first, which means we're going to look at this last part here. In other words, we just start off with a simple calculation that looks at the covariance between any 2 times t and s. So because the mean of the Brownian motion is 0, the covariance reduces to this quantity here. Typically we'd subtract the mean from each of these, but because the mean is 0, there's nothing to subtract. And once you write this down, all you need to do is apply the Tower property of conditional expectations to get to the hopefully the right answer. What we're trying to get to is this expression here. And we can do that by, for example, assuming that s is less than t, conditioning on w at time s, and the reason for doing this is that we want to carry out this expectation one step at a time. Right? If you want to evaluate this expectation here, you'd have to do it against the joint distribution function. What the Tower property allows you to do is to break down the computation into 2 parts. So here you condition on the past value. Now, because the thing that we're conditioning on is known, it comes out of the expectation. So that's the second step, is to take out what's known. That's another property of the conditional expectation. Now the next part is applies the martingale property and the Markov property, in fact. So I said applied the martingale property of the Brownian motion. This is sort of true. I mean, it's true, but it's ignoring the fact that if this is not the kind of true martingale property, or it's not the full extent of it. The full extent of it would actually condition on the entire path of the Brownian motion from 0 to time s. If we combine that together with the Markov property, then it suffices to condition on just w at time s. And then, by the martingale property of the Brownian motion, you have, the same result. In other words, the Brownian motion doesn't go up or down. On average, it stays the same. So once that's plugged in, you'll arrive at the fact that the covariance between time values t and s is in fact just the variance at time s, provided s is less than t. And so this part could be kind of crossed out and make this expected value squared is equal to the variance, which is equal to s. And this comes from the probability density function of the Brownian motion at time s. So we just ran this for s less than t. Clearly, if we were to attempt the same thing for t less than s, we'd get a very similar result. There's no reason to prefer t to s. And what we just see is that when we assume s is smaller than t, we get s. And when we assume t is smaller than s, we get t. So what's the final answer? The covariance between the two is just the minimum of the 2 times. And that's exactly what was asked for in this property here. So now we need to talk about whether W is in fact a Gaussian process. So again, we're allowed to assume these 2 properties because we're given a process satisfying them. How can we check whether W is mean 0 Gaussian? The mean 0 part seems pretty easy. You have a bunch of timestamps. You gather this vector, and now you need to check whether it has a multivariate normal distribution. And because every coordinate has mean 0, you know that that multivariate normal distribution has mean 0. The next part is then to basically argue that this distribution is in fact multivariate normal. That's not a priori clear. Now, we've computed the covariance, but that does not necessarily mean at this point in time that this vector actually has a joint distribution that's multivariate normal. The way to show this, so this is a little bit more detailed than what Ross provides, but the idea is the same. The idea is to write the vector, or every coordinate of the vector, in terms of different increments, and the increments are independent by this property here, which is going to help us. So each coordinate, as written here, can be written as the sum of the increments up to that point, and each increment is in fact normal with variance equal to the length of the time that has elapsed during that interval, which is ti minus ti minus ti minus 1 for each one of those things in the sum. And so what what this expression in terms of the increments is basically saying is that you can write every single coordinate as a sum of a bunch of normal 0, 1 random variables. They're all independent. All of them are multiplied by the square root of the length of the interval, and the reason is that each increment is normal with variance t minus s. What is that equal to? That's the same thing as taking the square root of the variance and multiplying by the normal random variable of mean 0 and variance 1. That's just a property of the normal distribution. If I multiply a normal 0, 1 variable by an amount sigma, the new thing I get is normal with variance sigma squared. And that's exactly what's done here. So what's the final conclusion? The final conclusion is that you can actually express the entire vector as some matrix A times this vector of 0, 1 IID normals. So in other words, every single coordinate has now been shown to be a linear combination of normal 0, 1 independent random variables. Therefore, right, that's the conclusion. For this matrix A, it defines the covariance matrix of the multivariate normal distribution of this vector. So you'll see a short argument from Ross to kind of to the same effect, and this spells out a few more details in the derivation. So what are these kind of conditions, not conditions, but definitions useful for? So, just one example, and you can kind of practice on your own, is they can show you how to describe various ways to express a Brownian motion in terms of another one. So these are, in some sense, properties of the Brownian motion, but in a way they're also defining a Brownian motion from another one. So we're going to start with W, which is a Brownian motion, and go through all of these kind of one by one. And for practice, you can try to prove each one of these statements by using definition 1 or definition 2. And you'll find that some of these properties will be difficult to prove with definition 1, and definition 2 will have to step in. And conversely, some will be difficult to prove with 2, and you'll use definition 1. So one property is symmetry. In other words, the negative of a Brownian motion is again a Brownian motion. So if I define Bt as a negative of Wt for every single point in time, I've just flipped my original Brownian motion over the x-axis, and there is a certain symmetry involved in the normal distribution that allows you to go ahead and verify, perhaps, these two properties for B, given that they held for W, and establish this symmetry property. Same thing works for something called time homogeneity, meaning that you can restart the Brownian motion at any point in time t. So we're going to fix some time horizon t. It's going to be a constant time that's fixed ahead of the fact. And then you're going to form this increment. In other words, what essentially happens is W evolves up to some point capital T, and then we sort of restart a new process from there. You basically subtract where the process was from, some new kind of beginning. The new beginning is marked at time capital T, and the process kind of evolves. And time homogeneity here refers to the fact that regardless where you restart the Brownian motion, we're restarting by subtracting off where it currently sits. The new process that's obtained, namely B, once again satisfies either these two properties or these two properties. Time reversal is an interesting one. This is a Brownian motion run backwards in time. So you're in fact going to subtract the endpoint and run time in a backwards fashion. So here the Brownian motion that results is only going to be valid on this time interval from 0 to capital T. Scaling is the next one. So this allows you to scale the Brownian motion by some number. This is 1 over the square root of c that I'm multiplying by outside. But you can see that additionally you have to adjust the time by a scale of c. So this allows you to kind of compress or expand time and the rate at which it perhaps evolves. You can think of a line of slope 1 as sort of a regular clock, and c times t is either going to accelerate time when c is greater than 1, and when c is less than 1 you're going to slow time down. So if c equals 1/2, you're running the clock at half the rate. But in order to actually scale time, you have to also multiply by this another factor outside, 1 over the square root of c, in order to adjust the properties in a way that b is still a Brownian motion satisfying either definition 1 or 2. Time inversion, this is an interesting one, where you're scaling by time on the outside and inverting time, the actual time scale. So when so near 0, you're basically out at time infinity, essentially. And as time moves forward, you're actually approaching time 0. Right? As t grows, 1 over t actually decreases. So this is, in some sense, similar to time reversal, but acts on the entire real line. So you're able to run the Brownian motion out from infinity back to time 0. And by the way, here time 0 would happen at t going out to infinity. So as t goes out to infinity, the new inverted clock, 1 over t, in fact goes to 0. And the last property is averaging. So this just allows you to take, let's say, n copies of a Brownian motion W, and then combine them in this kind of a convex combination type formula. So you're just summing them up and scaling each one by a constant ci, and provided the ci, or the squares of the ci, sum to 1, the new process that results, B, is once again a Brownian motion. So all of these can be shown by either definition 1 or definition 2, and depending on kind of the problem, one will be a little bit easier and another could be potentially even impossible. So we're going to look at some remarks about the world of finance and how what role the Brownian motion plays therein in the next segment. And for now I'll end this clip.